Hôm trước chúng ta vẫn ở cái phần introduction đúng không các bạn nhỉ? Chưa xong introduction đúng không? Okay, for nanomaterial, so you have to know what is the difference between nanomaterial and bulk material. And you know what is nanomaterial also, of course, what is a nanoscale material, so you have to know. And you have to know about the different property between nanomaterial and bulk. Okay? So and why are material? The property of material is so different from the bulk material. So you have to take note about the last side different behavior collision with atom when it's in atom or molecules scale, okay, and a small particle. So the behavior of atom collision in the nanoparticle will also different from the bulk material. So this will less many different property from the nanomaterial versus bulk material. Okay. Okay. And you also have to know is the nanoparticle have a very high fraction of the atom on their surface, or it means a free atom on the surface of a nanoparticle will be much larger compared to on bulk particle. Okay, so that's also make nanoparticle very active uh, powder. Okay, and at nano size, okay, at nano scales, other property, physical property of material also may be changed or modified. For example, energy bands or band gap, okay, also change at nano scale, and the density of state also change. For the metal is will be increased. So this will needs to increase electrical conductivity. So and okay, this history of nanomaterial and nanotechnology. So you have to look again, back again, and we have classified nanomaterial. Okay, so what kind of nanomaterial we have? So we can classify into 4 different kind of nanomaterial. Okay, 0D, 1D, 2D, and 3D. Okay, so we have here example of a nano material for 0D is mean 0 dimension here is for nanoparticle. Okay, and for fluorines or for buckyball. Okay, buckyball. And for 1D nanomaterial is, for example, nanofiber and carbon nanotube is including a single wall nanotube and a multi-wall carbon nanotube. Okay, we also have 2D nanomaterial, for example, graphene. Okay, I already introduce to you about this kind of material. So you will study this in in next lecture. Okay, about the some special nanomaterial, and the last one will be 3D nanomaterial. So for example, ceramic, porous metal. Okay, and please also remember that nanomaterial can be metal, it can be ceramic, it can be a polymer. Okay, so not only metal or ceramic. Okay, so for formation of nanomaterial, we have two approach, top-down methods, and we have bottom-up methods. Okay, so this is top-down methods is make scale down from micro to about 10 nanometer, and for bottom-up methods, synthesis cell of assembly from uh, molecules to a cluster, so the particle size of uh, uh, material synthesized by these methods can be in a range of 1 to 100 nanometer. So you can see is the nanomaterial synthesized by bottom up will give a smaller particle compared to top down methods. So in general, so we have this. Okay, I already explained to you what is a top-down methods. Okay, what is bottom-up methods. So in the exam, for example, maybe we have some question for you to distinguish, okay, the differences between top-down and bottom-up methods. Okay. And okay, so one of the very important topic in this lecture is what is the main property of nanomaterial or nanoscale material different from the bulk material. Okay, so last time we already I give already give him a briefing, okay, on this. Okay, so the reduction of of a material dimension. Okay, so this has been repeated for many times. Okay, so reduction of dimension of material, okay, has a pronounced effect on its physical, mechanical, and chemical property. Okay, and in most cases, through the value of this property are very different from the in the bulk. Is depending on the size and the morphology of nanomaterial. Okay, so this factor will affect on the property of nanomaterial. So we will go to detail in different property of nanomaterial. So one of the very important property of nanomaterial, which makes the difference from the bulk material, is surface area to volume ratio. Okay, so this is very important. So due to the small dimension, okay, nanomaterial have extremely large surface area to volume ratio. Okay, so sometimes we call it a specific surface area. Okay, so the large surface area to the volume ratio of nanoparticles is open many possibility for creating new material and facilitating chemical process. Okay, so it means because the surface of nanoparticle is have very high fraction of free atom on the surface of the particle. So you know that for any reaction happen, so it will it have to be contact. Okay, in the particle should be contact. So on the surface they have many free atoms, so it will be uh, easier to for chemical reaction. It happens when they in contact to each other. Of course, at the nanoparticle size, because the surface area to volume ratio is high, so it means the contact surface will be higher compared to the bulk material. Okay, so thus it make the difference between nanomaterial and bulk material. Okay, so that's why even metallic nanoparticle can be used as a very active catalyst. Okay, so they can use for chemical sensor. Okay, so I will give you one of topic for presentation is for uh, using or apply of nanomaterial for sensor. Okay, for chemical sensor. It also can be sensor for other application, not only chemical. Okay, for light sensor also. Okay. So from the nanomaterial scale for sensor, it will make the sensor is more sensitive, okay, work more precise, okay, and it can detect more in large range of different element or different material or gases, okay. And of course, you have to remember that a specific surface of the nanomaterial is uh, proportional to 1 over radius. Okay, so this how it make the surface increase when you divide the particle into smaller. Okay. Okay. This I already talked to you last week, so I just go fast. Okay, briefing. So because the nano material, okay, it have a very small scale. So the total energy of this material also increase with overall surface area. Okay, so it means that uh, when the material at nanoscale, so it will not stable. Okay, because the total energy or energy of the system increase. As you know that uh, the chain of the matter, okay, it exists in the nature it, with low energy, okay. So for nanomaterial with a high surface energy, so it will not stable. So this also challenges in the synthesis of nano material. Okay, so this table gives you the relationship between total space area, okay, with surface energy. So you can see the total space or the size, okay, the size of the material reduce and the surface energy will increase. Okay, so you look at this table. Okay, so this also can be come out in the exam. Okay, for asking you for relationship between surface energy and the particle size. Okay, and here this figure show you the ratio of surface atom. Okay, uh, surface atom is mean the atom on the surface of the particle. Okay, nanoparticle. So you can see, as you can see here, if the particle reduce, okay, so the surface atom, the percentage of the surface atom will be increased. Okay, increase. So this image nanoparticle are different from the bulk material. Mm. Okay, so due to the vast surface area, so all nanostructure material possess a huge surface energy. Okay, as I show you in the table. So in thermodynamic, called unstable or metal stable. Okay, unstable. So this will be challenge. Will be challenge. Okay, challenge for synthesis of nano material. Okay. The surface energy of nanomaterial can be defined, okay, gamma, okay. defined is as the energy required to create a unit area, okay, of a new surface. So this is the surface energy, okay, okay. Is dz to dA, okay. It depends on the temperature, pressure, okay, so on. So A is surface area, okay, surface area. Okay. So it means that if the particle small, okay, so the surface area reduce, so energy, surface energy will be increased, yeah, increase. Okay, to the next property of nanomaterial. So as a nanomaterial, many very strange phenomena can be happen. Okay, so the next one will be melting point. Okay, so normally maybe, okay, maybe you think that the melting point of the copper, okay, is always is the same or can be constant. For example, uh, yes, so the copper will be melting at the temperature of 1033 degrees C. Okay, in the bulk material. For example, you put one bar of the copper in the furnace and you melt down. So the temperature of melting of copper will be 1833. 33 degrees. Okay. So of course, maybe you also know that this temperature can be a little bit different with the impurity inside the material. Okay, so if we have very high, okay, purity of copper, okay, for example 99.999, okay, so four number, okay, or six number of purity. So the melting temperature can be 1083 degrees C. Okay. But the difference here is when the material or the copper become to nano scale. Okay, the melting temperature can it will not it will not the same anymore. Okay. Okay. In fact, the melting temperature of nanomaterial will be reduced. Okay, reduced when it's at nano scale. Okay. Okay. So here says generally the melting point of a box material is not depend on its size, okay, but for temperature, melting temperature of nanomaterial decrease with the increase in grain size, okay. So here the difference between nanomaterial and box material. Okay, and the decreased melting temperature can be on the order of tens to hundreds of degrees for metal with nano mass dimension. Okay, and the chain of melting point can be attributed to the last surface to volume ratio. Okay, so now you can see, okay, the specific surface, okay, will affect to the physical property of the nanoscale material. Okay. Uh, so you can see how it affect. Okay, and so because nanomaterial scale have a larger specific surface, okay, than bulk material, so it affects the thermodynamic property. Okay, so this is the reason why, okay, the melting temperature of nano scale material have lower, okay, compared to the same material but at the bulk, okay, bulk material or at the micro scale. Okay. So please take note this. Okay. And we go to the next property of nanomaterial. Okay, is electrical conductivity. Okay. So for electrical conductivity, okay, in general, is will decrease with the reduction of dimension. Okay, in general, okay, the electrical conductivity will decrease, okay, when reduce the dimension. Okay, so because so why, okay, why is reduced? Because the increased surface scattering. So it means at nano scale, okay, or nanomaterial. So material will have higher surface area, okay, or we can say it have higher specific surface area, okay. So it means the boundary, okay, of the particle, okay, volume of boundary in the nanomaterial is increased, and of course the boundary will act as to scatter, okay, to scatter, okay, the charge carrier, okay, when they come to the boundary. So this will reduce electrical conductivity. Okay, so this is why, okay, this explain why, okay, electrical conductivity decrease. So this involves to the increase of surface scattering of charge carrier, okay, charge carrier. Okay, so of course because of scattering, so the mobility of charge carrier will reduce, so will lead to the reduction of electrical conductivity. As you may know, that electrical conductivity is decided by the concentration of charge carrier and their mobility. It means if mobility is can be sorry, the charge is can be a charge carrier can be electron, can be the hole, or yes, and so on. And this charge have to move. Okay, so it can be it will create a current. Okay, so if charge carrier is difficult to move, so it means this material have a high electrical resistance. Okay, it means electrical conductivity small. Okay, so because increase surface area, so make it so it's scatter, okay, scattering or scatter charge carrier. Okay, so uh, that is an explanation. And now one more thing is also about the band gap, okay, can become a wire, okay, and conductivity decrease and density of state also decrease. So this may also happen, okay, in the second one. So but the first this is the first factor very important, okay, effect on the electrical conductivity as nanoscale. Yeah. And is can be increased, okay. However, in some special case, okay, electrical conductivity of nanoscale material can be increased, okay, due to the better ordering in microstructure or nanostructure, okay, nanostructure. Yeah. For example, polymetric fiber, okay, and of course for other material, for example, nanotube, carbon nanotube, it can be, it will be, okay, electrical conductivity will be higher, okay, in that scale, okay, in that phenol, yeah, in that scale, okay, And maybe you also know that for graphene, okay, graphene, okay, electrical conductivity and thermal conductivity very high, okay, very uh, or you can call it extremely high, okay, compared to is at the form of graphite, okay, graphite, okay, it's a form of graphite. So from the graphite, thermal conductivity and electrical conductivity is low, okay. So by we attach, okay, to one layer of graphite, okay, so it's become graphene. So this at this kind of nano scale, okay, so thermal conductivity and electrical conductivity will become extremely high, okay, extremely high, okay. And nano material can be used very good separate place in a battery, okay. So this also will be one of the topic for you to study and present, okay. Uh, okay, after midterm break, so you will present, okay. So because nanomaterial, okay, is very good for battery application because it have a high surface area, so it and can increase the exchange, the charge carrier between cathodes and anodes, okay. So it will increase the electron current, okay. So that's why, okay, nanomaterial have very high potential application for battery, okay. So now scientists and researchers, they focus on the improving of battery based on nanomaterial, okay, and nanoscale. Mm. Mm. So one day structure such as nanowire, nano tooth conduct electrical current, yes, differently compared to a buck conduction, as I mentioned you in a carbon nanotooth or even in a 2D for graphene. Okay, so this. Mm. Okay, so for the next property will also affect or different behavior as nano scale material. It also very important. That's a magnetic property. So the behavior of the magnetic property at nanoscale is will be different. Okay. Uh, so this also open many application in uh, memory. Okay, memory system. Okay, and other system also. And the magnetic property of nanomaterial depend strongly on size of nanostructure material. Okay. Okay. And you can see ferromagnetic particle become unstable. Okay, unstable and can switch polarization direction and become paramagnetic. Okay, you can see here. Okay, this is paramagnetic. Okay, paramagnetic. When this vector is not in the same direction, so we call it a paramagnetic. Okay, in the bulk material. Okay, this behavior. Okay, it can the magnetic vector. Okay, can be any direction. Okay, okay. So the magnetization get a maximum, okay, value at this at bulk material. Okay, so what happened when we scale down to nanoparticle? Okay, so first of all, here maybe is one, okay, one vector of magnetization can be stored in one, okay, one nanoparticle. So it's very difficult to change the direction in this kind of at this scale. Okay, at this scale, it's very can make change the direction because it already is one magnetized vector uh, uh, be stored in one particle. Okay, so it's not easy to change the direction freely. Okay, so that is a difference in from the bulk material and nanoscale material. Okay, and and the magnetization vector of different domain. Okay, so one vector in this we call this a one domain. Okay, one domain. So this the domain in nanoparticle in one particle is applied as a one domain. Okay, one domain, and only contains one magnetization vector. Okay, so one domain, and so is the domain in sample are not are all parallel to each other. Okay, and so overall magnetization is decreased. Okay, okay. So here are the different parallel. So in after break, okay, after midterm breaks, okay, Dr. Bing will teach you more detail in this property, okay, in material. Okay, the next one will be optical property, also very strength in nanoscale material. Okay, the optical property are governed by a quantum confinement. Okay, the optical quantum confinement. Okay, for a smaller the particle, the shorter wavelength in absorption spectrum. Okay, so smaller particle, so shorter wavelength absorption. Okay, and the color will shift from red to blue. Okay, you can see here just by changing the nanoparticle size or even nano particle shape. Okay, geometry. Okay, so will the color, the absorption of spectrum will be different, and of course it will be make a different color. Okay, different color you can see here for different nano particle size here from reduce from 5.5 nanometer to 2.3 nanometer. So the particle the color, okay, will be changed, okay, from red to blue. Okay, you can see here, and here this paragraph show you the behavior of the absorption of the spectrum for different nanoparticle for the same material, but different the geometry. Okay, so the absorption behavior also different. It means they will observe different wavelength. Okay, so here for the cross, okay, cross nanoparticle, this is a sphere nanoparticle. Okay, the cross nano, the rod is not particle, sorry, the rod nano material. Okay, or we call it a nano rod. Okay, nano rod. Okay, this is nanoparticle. Okay, so we can see here the big absorption of the light will be different when it change. Okay, change the shape and the size. Okay, okay, this is same with the rod. Okay, but the change size. Okay, so the absorption of light are also different here. Okay, you can see here, and it's different for particle and different for rod, nano rods. Okay, so this also very interesting. Okay, property of nanomaterial. Okay, so optical property of nanomaterial depend on feature of size. Okay, shape, shape, surface, characteristic. Okay. Okay, so remember this. Okay, when you will ask for the effect or of what's the factor effect on optical property of nanomaterial. So you have to know this factor will affect on the optical property of nanomaterial. So this can be for some for question, okay, multi-choice, okay, multi-choice question. Okay, the last one maybe I want to introduce you here is mechanical property also. This is also very important property for material, especially for metal and composite material. Okay. So you can see here this is a hardness of metal, okay, and intermetallic alloys as a function of grain size, okay, in nano phase material. Okay, here is a hardness. Sorry, here is grain size of nanoparticle. Okay. So this mechanical property of material is will be determined by the size of particle as a Hall-Pest equation. Okay, a Hall-Pest equation. Okay, so in this equation is stated that the hardness of particle increase with a decrease of the size of the grain. Okay. Okay. Hardness. Okay, is the strength or the strength of material. Okay, is so here the relationship. Okay, I forgot to put the equation here, but you can okay, you can take it from literature. Okay, literature or from other source. Okay, other material. It's easy. You can Google. Okay, also easy. Okay, here, okay, you can see, okay, this is the 1 over square root, 1 over square root of the grain size, okay. Okay, here the hardness, okay. So here in this scale, show you the particle size, okay, particle size, 115 and 5, okay. This is scale in nanometer. So we can see here, okay, when the grain size, okay, grain size of the material reduce, okay. So the hardness of the material increase, you can see here. For example, okay, so for copper, okay, for copper, what is the micro hardness of copper here? Here, okay, you can see here this. No, here, this micro hardness of copper, okay, you can see here is around uh, 2 gigapascal, and the hardness will be increased when the particle size reduced from 100 nanometer to 5 nanometer. You can see here. Okay, you can see this. And also, for example, other iron. For example, iron. Okay, iron. Of course, is the micro hardness will be higher compared to copper. So we can see here for the same nanoparticles. Size, okay, for example, iron have around 4, okay, around 4 gigapascal, but copper around 2 gigapascal, okay. So anyway, you can see the micro hardness increase with reduce the particle size, okay. So that's why the scientists or researcher want to scale down, reduce um, uh, the grain size, okay, or particle size of material in order to increase hardness and strength, okay, of material, especially for metal and for composite material, okay. Okay, this is all for introduction. Okay. So, any question or discussion you want to discuss here before I move to the next topic or next lecture? No? Oh, okay. Okay. So I thought you are sleeping. Okay, so we so this introduction very important. Okay, so you can have general look on the nano material. Okay, nano scale material. We go to next one will be zero. Okay, zero D nanomaterial scale is mean nanoparticle. Okay, so we will study about nanoparticle. Okay, this lecture will cover on zero-dimensional nanostructure is nanoparticle. Okay, so in this lecture, I will show you how to synthesize nanoparticle. Okay, what is the method to synthesize nanoparticle? Okay, and how we can control nanosize. Okay, of nanosize of material. Okay, how to make to control it uniform. Okay, and how to make it small. Okay, so this is using the reference book, okay, nanostructure and nanomaterial, okay, synthesis properties application. The author is Zhang, okay, so you can find this okay book for reference. Okay, so we go to again. I just give you okay, remind you again about the synthesis or fabrication methods for nanoparticle. So in the introduction, I already tell you about the production or synthesis methods for nanoparticles. So we will have two approaches. Okay, one is top down. Okay. So in this lecture, okay, the top down methods, okay, for synthesis or what is chatting? Top down particle will synthesize, okay, or fabricate by high energy mechanical alloying. Okay, what we call it by a bone milling machine. Okay, bone milling machine. Okay, and by lithography methods. So these two common methods to for top-down methods. So in this lecture, I will teach you about milling. Okay, about milling, bone milling machine, or normally we call it high energy energy. Okay, bone milling. Okay, so this kind of this is an apparatus of bone milling. Okay, we can produce nano scale
You haven't
material.
shared your slide.
Oh, okay, sorry. Oh. Where is this? Oh, no one tell me. Okay. Is this okay now?
Yes.
Okay. Sorry. Okay. Okay. So this is the book. Okay, you can capture screen. Okay, or you can write down, take notes for the reference. Okay. Okay, this is a book. Okay, I talk about. Okay, okay, this top-down methods. Okay, so we use high energy bone milling. Okay, to fabricate nanoscale material. Okay, this okay, in this case is nanoparticle. Okay. So high energy bone milling can produce nanoparticle trains from a couple of tens to several hundreds of nanomaterial in diameter. So as I mentioned, that this kind of methods can be given you in a wide range of particle distribution. Okay, is not really uniform. Okay, so these are the disadvantage of this methods. However, is this method very simple. Okay, so many research and scientists they still want to use this kind of apparatus to produce nanoparticle. Okay, and it also have many different advantages. I will show you in when we go to this kind of apparatus, okay, or equipment. Okay, okay, here. So nanoparticle produced by high energy bone milling have relatively broad side distribution, okay, and vary particle size or geometry, okay. So this the broad side distribution. This is the main thing, main background of this, okay, or disadvantage of this methods. Okay. Oh. Okay. So this figures show you the behavior of ball and okay, a ball and container. Okay, during rotation. Okay, rotating. Okay, and this is the behavior interesting between the ball. Okay, and powder particle during ball milling. Okay, we call ball milling. The white circle here is ball. Okay, this the black sphere here, particle here is powder. So yeah, so this many behavior interaction between ball and a particle during ball milling. I will show you later. Okay. Uh, uh, and you also remember that this kind of approach also contains some significant amount of impurity from milling medium, okay, and defect uh, result, resulting from milling, okay. Of course, we can have some techniques, okay, to reduce the impurity from milling medium. Okay, we will have some technique by we choosing some kind of medium is have a high harshness or high resistance. Okay, so by using zirconia oxide, okay, instead of using stainless steel bone or stainless steel container. Okay, so we using zirconia oxide, so we can reduce this kind of impurity. Okay, from a container or from a bowl to our powder. Okay, our material. Okay, so this is and and such a prepared nanoparticle are also commonly used in the fabrication of nanocomposites. Okay, so this for nanocomposites very commonly people use bone milling. Okay, or we call it high energy bone milling. That's why we call it a high energy bone milling, because this machine can rotate with a very high rotation speed. Okay, very high rotation speed. So the energy is introduced to the powder is also very high. Okay, so we call it high energy bone milling. Okay, so this is very common to use this kind of machine to fabricate nano composites and nano grain size, okay, material with very low synthesized temperature. Okay, this is the advantage of this kind of machine, okay, and equipment. Okay, and uh, and also by using this kind of equipment, okay, the particle or for the composites, okay, for different composition will be it will get a very homogeneous composition, because the element can mix very homogeneous, okay, mixing, okay, very homogeneous mixing powder, okay, by using this kind of equipment in case fabricates nano composites. And of course, we, as I mentioned here, you can synthesize nanoparticle at low temperature. Okay, so this low temperature can keep the material at a small size. Okay, you know that when temperature increase, of course, particle size also increase. So it's difficult to control. Okay, the particle size at high temperature. Okay, so by this kind of advantage for this machine. Okay, for nano composites and nano grain size box material, the defect may be anneals. Okay, here I said is after ball milling, the material can contain defects. Okay, so by annealing, okay, after synthesize, we can remove, okay, uh, remove the defect structure of material. Okay, and we may also control the size distribution, okay, particle shape by annealing, okay, and small amount of impurity are relative insensitive for application. For example, for mechanical application, a small amount of impurity is can be negligible. Okay, it means relatively insensitive. Okay, insensitive. Uh, okay, for their application. Okay, so in case of mechanical application, but for the physical or optical application, okay, small amount of impurity will very sensitive. Okay, very sensitive for their application. Okay, for the second approach is bottom up. Okay, this bottom up approach are far more popular in the synthesis of nanoparticle, and many methods have been developed. Some method very popular, some is not. Okay, some very high efficiency. Okay, and example, nanoparticles are synthesized by homogeneous nucleation from liquids or vapor or heterogeneous nucleation on substrates. Okay. So in this lecture, I will teach you about synthesis of nanoparticle using homogeneous nucleation. Okay, from liquids. Okay, so this will be covered in this lecture. Okay, there are many methods, so you have it cannot be covered in this lecture. So you can read the book. Okay, you can read from the book for the reference. Okay. Nanoparticle or quantum dots can be also be prepared by phase separation, okay, through annealing of appropriately designed solid material at elevated temperature. Okay, these are for second method. So and nanoparticle can be synthesized by confining chemical reaction. Okay, nucleation and growth process in a small space. Okay, so have many techniques or methods to synthesize. Okay. Okay, so and we also can group various synthesize method into two categories. Okay, one is we call it a thermodynamic equilibrium approach. So in this lecture, we will go to this approach by this approach and a kinetics approach. So for the thermodynamic approach, synthesis process will consist of the generation of supersaturation. Okay, this is the first step. Okay. The second stage, okay, second stage is about nucleation. Okay, the last stage about subsequent growth. Yep. So this is will be for thermodynamic approach, and we will study in this lecture. Okay. Here something you have to take note, okay, before we go detail on the synthesis process. For the fabrication of nanoparticles, a small size is not only the requirement, okay. The processing condition needs to be controlled below characteristic. Okay, one is you have to identical particle size or uniform particle size. Okay, this is very important. So we want to synthesize some particle with uniform size. Okay, so this is the thing we have to control. Okay. During synthesis, okay, during synthesis material. Okay. The second thing you have to take into account, okay, take into the mind the identical shape or morphology. So we want to synthesize all the best, okay. The material have the same shape or the same morphology. Okay, it means identical shape and morphology, because it's on effect on the property as I mentioned before. So we want to control, okay, this shape and morphology as we want. Okay, so if we cannot control the shape and morphology, so the property can be different from which we want to design, okay, which we want to aim. Okay, and the third is identical chemical composition and crystal structure, also very important. Okay, so after synthesis, we want to have, okay, identical chemical composition, okay, which we design at the beginning before we start synthesis. Okay, so after synthesis, we want to have the chemical composition the same with we design the experiment. Okay, and we have to have crystal structure. Okay, identical crystal structure. Okay, this can be cubic. Okay, it can be uh, uh, hexagonal and so on. Okay, but it have to be identical. Okay, a crystal structure. Okay, and the first one is individual disper or mono disper. Okay, no agglomeration. Okay, no agglomeration. This is also very important because the particle size, nanoparticle size, they intend to stick together. Okay, so it will become a big cluster or big particle. So this also affect to the property of material. So all of these things you have to take into your mind, okay, before we design or we synthesis, okay, synthesis nano particle. Okay, so for nanoparticle in this discussion or in this lecture, it can be includes a single crystal, it can be polycrystalline, it can be amorphous particle. Okay, is with all possible morphology such as sphere, cube, and plates. Okay, so remember that. Okay, all these things. This can be covered in this topic, not only about single or polycrystalline material or amorphous particle. Okay. Okay, we go to the first approach to synthesis nanoparticle is a homogeneous nucleation nanoparticle synthesis. Okay. For the formation of nanoparticle by homogeneous nucleation, okay, a supersaturation of close space specs must be created. Okay, saturation. Okay, difficult to pronounce this word. Okay. So it will be over, okay, over solubility. Okay, is over solubility, so we call it super saturation. Okay, super saturation. Okay, and a reduction in temperature of an equilibrium mixture such as a saturated solution would be less to super saturated super saturation. Okay, so this temperature, okay, reduced temperature. In this case, is involved to synthesis by liquid, as I mentioned before. Okay, and for the formation of metal quantum dots in the glass matrix by allowing a moderate temperature, a good example of this approach. Okay, so the moderate temperature should be suitable for this kind of synthesis. Okay. Before discussing detail on of the approach, okay, for the synthesis of uniform, okay, uniformly sized mono is means single, okay, dispersed nanoparticle. So we will first review on fundamental homogeneous nucleation, okay, fundamental homogeneous nucleation, and subsequent growth, okay, subsequent growth. It means after it's already formed nucleation, okay, and then nucleation will be grow into a particle, nanoparticle, okay. So this is two process, okay, three process as I mentioned before, okay. Solution synthesis of metallic, okay, semiconductor or oxide nanoparticle we'll also discuss in detail. Okay, so after I give you the fundamental of methods, okay, then we will give you some example synthesis of some material, okay, example, okay, based on this method. Okay, so vapor phase reaction, okay, and solid phase separation for formation nanoparticle also include in this section, okay. So, but the most important here in this is cover this content, okay. So we will go in detail. Okay, the first one we have to go is fundamental of homogeneous nucleation. Okay, homogeneous, because we want to have a uniform, okay, particle. Okay, so here the first thing we have to know about the fundamental of the nucleation. What we call is homogeneous nucleation. When the concentration of solutes in solvent exists is equilibrium solubility, okay, or the temperature decrease below the phase transformation point. So a new phase appear, or a new phase have to be uh, uh, occur, okay, because when it exists equilibrium value, so it means the energy of system will be increased. It means the system will not be stable anymore. So to reduce the energy of the system, so they have to form a new phase, okay. So that's why we have to have the solution with uh, what we call is a super saturation, okay, to form this kind of nanoparticle, okay. Okay, here I also stated here. So consider the case of homogeneous nucleation, okay, of a solid phase from a super saturated solution. Okay, so that's why we need to have a super saturated solution to synthesize, okay, nanoparticle. Okay, okay, so this because okay, this is the fundamental, okay, for this approach. Okay, you have to remember. So a solution with a solute existing the solubility or super saturation uh, processes a high with free energy. Okay, as I mentioned, it will give you the energy of the system. Okay, will be increased, so let to, okay. So the overall energy of system would be reduced by, okay, uh, separating a solution from a okay, solution from solution. Okay, it means that by reduce the energy of the system, it will be make new phase, or if make separation, okay, solution from solution to make okay particle, okay, make particle. And please remember that, okay, when the particle size increase, okay, or the surface of particles increase, so the energy will surface energy will reduce. Okay, so by is segregating, okay, to form particles, so the surface energy will reduce, so the energy of system will be reduced. So this is the fundamental, or we call it this is a driving force, okay, driving force to form a nanoparticle. Okay, okay, maybe we take a break for 15 minutes. It's okay.
Yes.
Okay, so
Yes.
after break, breaking time, if you have any question for discussion, so okay, so we will do it after break. Okay, we continue. Okay, everyone ready?
Yes.
Okay, we go back. So please, when you can watch the lecture again. Okay, by we already record this lecture, so you can see slide also. Okay, and of course you can watch my discussion on this lecture. So I will try to go slowly, okay, as possible. So I try to make you easy to understand. Okay. So, but if anything you feel confused, you can ask question. Okay, you can interrupt me for question. Okay, so this is the fundamental of these methods, and also this is a driving force for the formation of nanoparticle. Okay. So here, this figure show you the reduction of overall give free energy of supersaturated solution. Okay, by forming a solid phase. Okay, so and maintains an equilibrium concentration. Okay, in solution. So this is a free give energy. Okay, for the solution. Okay, so after this can be made super saturated solution, and by making new phase. Okay, so the give free energy can be reduced. Okay, so this is a driving force. Okay, driving force for the formation of nanoparticle. Okay. Okay, here. Okay, so we call this reduction of heat free energy is the driving force for both nucleation and growth. Okay, as I explained. Okay. The change of give free energy per unit of volume of the solid phase delta Z, okay, is depend on the concentration of the solute. Okay, the concentration of solute. Okay, so take note this one. Okay, so this is the formula how the give free energy involved to the concentration. Okay, and the temperature and the volume of the atomic. Okay, so this delta Z, okay, minus kT omega log C per C0, so it's equal to minus kT omega log 1 plus sigma. Okay, so here C is the concentration of the solute. Okay, C0 is the equilibrium concentration of solute. Okay, K Boltzmann constant, T is temperature. Okay, omega volume of atomic volume. Okay. So sigma can be defined here. Sigma can be defined as by C. Okay. C, this one not C minus C, this one C minus C0. Okay. Per C0. Okay. So here, so use a relation shift. Okay, between energy, give free energy, and solubility. Okay. So we can control all of this thing to make to change. Okay, the energy. Okay, so from that equation, you can see without supersaturation, okay, example, sigma equal to 0, okay, 0. So it means delta Z equal to 0, okay, 0. So no nucleation. Okay, so no nucleation occur, okay. And when C larger than C0, so delta Z, okay, give free energy is minus, okay, or is smaller than 0. So nucleation occurs spontaneously. So this you already study, okay, and for chemical reaction, right? So for delta Z minus, so the reaction will spontaneous occur, right? Okay. So by control this solution, okay, so we can make the formation of nanoparticle. Okay. Assuming a spherical nucleus with a radius of r. Okay, so now we will go detail how detail the formation process of nucleation. Okay. Okay, so what is the condition for okay, we go in detail. Okay, and so the radius of r and the chain of give free energy or volume energy, we call it delta nu v here. This can describe by delta nu v here equal to 4 3 p as cubic, okay, and delta z, okay, here can be this is volume, right, plus with delta z, okay. So we have this one. Okay, so however, this energy reduction is counterbalanced by the introduction of surface energy. Okay, reduction by introduction of surface energy. It means when the particle is formed or nuclear instantly occurs, so it's more surface can be formed, and of course more surface forms, so the energy will be reduced, okay, reduced. Okay, so this what we call is introduction of surface energy, so can reduce energy. So according to the formation of new phase, okay, so by formation of new phase, so we can reduce the energy of the system, so the system will be more stable. So that is the driving force for this synthesis, okay. So this result in and increase the surface energy. Okay, we can formulate as this formula delta nu s, okay, equal to 4 p r square and gamma, okay. This increase surface energy, okay, of the system, okay. So this gamma is the energy surface energy per unit area, okay, unit area. Okay, in general, this one can be increased because it's particle form, so it can be it will make the energy surface, but in general, it will be the energy of system will be reduced by inform this particle. Okay, even this happens, so it means delta nu f will be smaller than delta nu v here. Okay. Okay, the total change of chemical potential for the formation of nucleus delta Z given by this, okay, delta nu V, okay, delta nu S, okay. So this equal to this one, okay. So this will this delta Z or free energy of this system will proportional to the radius of nucleus. Okay, you can see here. Okay, you can see it here. So it's proportional to the radius of the nucleus. Okay. So you can see here, people plot, okay, the energy of the system versus the radius of nucleus. Okay. Okay. This energy, surface energy. Okay. This total energy. This one volume energy. Okay. So volume energy here. Okay. Have this formula. Okay. So this is a total energy delta Z. Okay. Equal to this equal to energy of surface and energy of the volume energy. Okay. So you can see here with the radius. Okay. Of radius of the nucleus increased. Okay. And the energy of the system also increased and is often a maximum, okay, value as the radius star here. Okay. And then if we further increase, if the particle further increase radius, so the delta Z or energy of the system will rapidly decrease. Okay. So the R star here we call it a critical radius of the nucleus particle. So it means if the nucleus or nucleation, okay, want to exist or want to grow, so it's the radius have to be larger than a critical value. So you can see here after R star here. So the energy of system drop rapidly. So this means the particle will spontaneous growth. Okay, we don't have to interfere in the system, so the particle can grow freely. Okay, because the energy of system is reduced. Okay, so this. Okay, so R star here we call it critical sign. Okay, for growth of nucleation. Okay? Nucleus. Okay, so a nucleus with a radius smaller than R star, so will be dissolved in the solution to reduce the overall free energy. Okay, so only the nucleus have radius larger than R star, so it can be exist in the solution and it can be grow up to a bigger particle. Okay, so this is the fundamental. Okay, the mechanism. Okay, how the particle is formed and grows. Okay, for a nucleus with the radius larger or equal to R star will be stable. Okay, you see the energy will be reduced, so it's stable, right? Okay, and continuous to grow bigger. Okay, this is very important. So you have to take note this one. This is a okay mechanism of the synthesis. Okay, by solution. Okay, so you process by yourself. Okay, you can understand. Okay, so you can see this. Okay, here you can see the surface energy term increase, but the volume term will be decreased also rapidly. So the total energy will be reduced. Okay. Okay. At the critical sign, okay, of nucleus R equal to R star here. Okay, so we have the delta Z to dr equal to 0. It means at the equilibrium, okay, condition. Okay, so the critical sign R star, okay, and critical energy delta Z star will be defined as this below. Okay, formula. So for R star will be equal to minus 2 gamma, okay, divided to delta GV, okay, and delta Z star equal to 16 pi, okay, delta divided to 3 delta G square, okay. So this is the formula for critical sign and critical energy for the formation of nanoparticle, okay, or the formation of nucleus, okay, before it can continue to grow, okay, into nanoparticle, okay, even bigger, okay, can be a micro. But anyway, only the particle have the radius equal or bigger than r star, so it can be exist on the solution and can be continue to grow. Okay. Delta Z star here is the energy barrier. Okay, barrier that a nucleation process must be overcome. Okay, and R star represent the minimum size of stable spherical nucleus. Okay, minimum. Okay, minimum. Okay. So if smaller, so it will dissolve into the solution. Temperature also can influence the surface energy gamma. Okay, other possibility includes use of different solvent, okay, to add in the solution, and additive in solutes, okay, and the third one we also can make the reduce in the surface energy by incorporation of impurity into solid phase. Okay, so this is other methods we can reduce the energy phase. This figure shows the effect of temperature on R star and delta Z star of spherical nucleus. Okay, this delta Z, this one particle radius R. Okay, so supersaturation increase with decreased temperature. Okay, decreased temperature. Okay, you can see here with temperature reduce. Okay, so the energy, okay, surface energy, okay, also or the energy of system also reduce. Okay, so this is the increase of temperature. Okay, this is energy of the system with different temperature. We have temperature T1, T2, T3, so and TE. Okay, so here if T is so high, so we cannot find, okay, this is the maximum, where is the maximum energy, or when the energy will reduce. Okay, so of course for this temperature the nucleation process will not be happen. Okay. T, okay, so reduce. Okay, so temperature reduce, so the energy of system also reduce. So you can see here the R star of T3 will smaller as the temperature of the system are smaller here. So it means this easy to form particle, okay, at this temperature. So higher temperature, it means the nucleus have to often bigger in order to stable and to grow up. Okay, so with increased temperature, so the R star will be okay, have to bigger. Okay, R star have to bigger. Okay, in order to stable. Okay, or dissolve. Okay, stable and growth. Okay, the rate of nucleation per unit of volume and per unit time, what we denoted here is Rn. is proportional to process 1 I. Okay, we to the probability. Okay, P. That thermodynamic fluctuation of the critical energy delta R. So this is probability will be equal to, okay, proportional to delta Z star. So it means delta Z star here is if small, okay. So we can the proportion probability of the we can find, okay, nucleus in the solution will be higher, okay, and also for reduce the particle, okay, reduce particle. Reduce temperature. So it means more nucleus can be formed, okay, when delta Z star is smaller or temperature is reduced, okay. So this I mean. The concentration of solutes increase at a function of time. Okay, here we can plot the concentration of solutes. Okay, this concentration of solutes. This is a time. Okay, of concentration of this solute. This is time. Okay, and you can see here that, okay, this is for concentration of solutes in order to form nucleation and growth. Okay, so it have to get a minimum values, okay, in order to nucleate or to continue to grow. Okay, you can see here. So if no nucleation would occur even above equilibrium solution, okay, so no no nucleation can occur, okay. So the nucleation occur only when supersaturation reach a certain value above solubility. So this is they will get this value, okay, this value, okay, in order to form okay, to form a nucleus. Okay. So this is which correspond to the energy barrier, okay, in the equation, okay, 3.6 for the formation of nucleus. Okay. This one is corresponding to delta Z star, okay, or corresponding to R star also, okay. Okay, this is time. So after, okay, if you can see from this graph, okay. So after sometimes when the solution, okay, or solution can obtain a certain value, or we call what super saturation value, okay. So the nucleation will occur, and after a time, so this will really grow up particle, okay. So this is this graph, okay, so is the relationship between solutes, or it means after it form nucleation and grow, so the solutes concentration will be reduced. You can see here because the solute concentration is now incorporated to the particle, so it will be the concentration will be reduced. Okay. Okay, so after initial nucleation, the concentration or saturation of the growth species decrease, okay, and the chain of gift-free energy reduced. Okay, so it means the particle will grow up. Okay, when the concentration decrease below this specific concentration, okay, at a certain value, okay. So which will correspond to critical energy, and no more nuclear would form. Okay, so no nuclear form, but particle continue to grow. Okay. So here what we call is the growth will proceed until the concentration of the growth species have attained equilibrium concentration or solubility. Okay, so this is the process after it obtains a certain value of solubility. Okay, this just schematic so use a relationship between the formation of the solid phase. Okay, it means particle. Okay, involved to what's called here the concentration of solution. Okay, solution. Okay, you can see this. Okay. For the synthesis of nanoparticle will with uniform size distribution. So it's best if all nucleus are formed at the same time. Okay, so this is you have to take note that. Okay, take in your mind that. Okay, when you design the process. Okay, you have to take mind that in mind that the synthesis of nanoparticle with uniform size. Only can often, not only can be obtained by all nucleus are formed at the same time. Okay, at the same time. Okay, at the same time. So of course, for all the same time, so it will be the growth process will be equal, and the diffusion from solute to the nucleus also the same. So the particle will be grow up with the same size, okay, or similar size, okay. Because if the nucleus form after the first one, so the first one have more chance to absorb, okay, absorb the solute, so the particle will grow up bigger compared to the later form, okay, the later formation. In this case, all the nuclei are likely to have the same or similar sign, okay, since they are formed under the same condition, okay, as I explained to you. In addition, all the nuclei will have the same subsequent growth, so that's why particle is have similar or the same particle. Consequently, monocyte, okay, nanoparticle can be obtained. Monocyte is mean almost all the particles have the same size, okay, and it is highly desirable to have a nucleation occur in very short periods of time, okay. So if it happen in very short period of time, it means so it's no more, okay, addition of formation of nucleation, okay. So this go. So in practice, okay, in practice, to achieve a sharp nucleation, it means a nucleus can be formed rapidly, okay, or from with very large amount, okay. The concentration of the growth pieces is increased abruptly. It means rapidly increased, okay, to a very high supersaturation, and then quickly brought to below a minimum concentration for nucleation, okay. Yeah. So this is to obtain a sharp nucleation, and below this concentration, no more new nucleus form. Okay, so all the nucleation is formed at the same time. Okay, so we have no more nucleation form after this. So all the particles have grow up with the same condition. Okay, so that's the particle have a uniform size. So the existing new nucleus continue to grow until the concentration of the growth species reduced to equilibrium concentration. Okay. Okay. So this why we want to make the concentration okay, increase roughly, okay, and bring up to a minimum concentration, okay, quickly cross, okay, below the minimum concentration. So that's why we can achieve uniform size or mono size of particle. Okay, so we go to the next. Okay, to the next. I think maybe we stop here. We will discuss about the homework. How many minutes? Okay, maybe we still have 20 minutes. So maybe we I go. I finish this topics and then we go to the homework later. Okay, maybe. Okay. Okay. This subsequent growth of nucleation. Okay, so after it creates or it form nucleus, so the sequence, the next step, the nucleus will be growth. So we will study this stage. Okay, so we will study how it grow up, or so from that. From knowing this process, we can control, okay, the particle size. The size distribution of nanoparticle is depend on subsequent growth process of the nuclear. Okay. The growth process of nuclear involve multi-step, and the major step will be below. Okay. The first step will be generation of growth species. Okay, the generation growth, and the second one is diffusion of growth species from a bug to growth surface. The second process will be involved to diffusion. Okay. And the third one will be the absorption of growth speed on the growth surface. Okay, growth surface. And the fourth one will the surface grow through irreversible incorporation of growth species onto the solid phase. So this is 4 step, okay, of growth nucleus. Okay, this is 4 step, okay. Generation, diffusion, absorption, okay, and surface growth. So this is 4 step, okay, 4 step. And this step can be further grouped into 2 processes. The first one is supply the growth speed search to the growth surface, okay, and what we call is diffusion process. Okay, so we have a diffusion process is including generation, diffusion, and absorption growth speed onto the growth surface. So this process will involve to diffusion. Okay. The second process is involved to incorporation of growth species absorbed, okay, on the growth surface into a solid structure. Okay, this is and what we denoted here as a growth. So we have two process. One is diffusion, the second one is a growth process. Okay. We have a growth of process. Okay, so we go to the first process. Okay, to control the growth controlled by diffusion process. Okay, okay, we go to the first process. Okay, so we stop here. Next week we will continue with this. Okay, and now we go for discussion about the homework. Okay. Okay. So any questions so far? Any question? No question. Okay, so we will go to okay. Chami already got the list, okay, of the group. Okay. Okay. So what? Let's see what we have. Okay. Okay, can you see the presentation topic here?
Yes.
Anyone? Okay.
Yes. Yes.
Okay, thank you. So I will divide to several topic. Okay, so you can choose whatever in this. Okay, even you can propose topic by yourself. Okay, but anyway, this week and next week we have to finalize the group. Okay, we have to finalize the topic for each group. Okay, so in this week, okay, I will show you what you have to, what is the content of the presentation and the homework. As I mentioned before, the homework and presentation we will combine in one, okay, at one. And so here I am, I give you some the requirement or what is the content you should include in your presentation. And okay, so you will present on the topic on nanoscale material. Okay, so you can choose the nano material. Okay, you want to you feel interested. Okay, you feel interested, you want to present. Okay, you can choose by yourself, but here I give some suggestion. Okay, some topic for you. Okay, consider. Okay, so for the presentation content, okay, you have to cover several requirements here. Okay, you have to you have to show, okay, what is the crystal structure and property of material you present, okay, and you have to show what is the application of this nano material and how it work. It mean, yeah, it work for the application, okay. For example, if you want to a certain nanomaterial for biology application, so you have to explain how this material is work for health application, or how this material can work for bone replacement, okay, or if you want to choose nanomaterial for battery application, so you have to explain how this nanomaterial can work for battery, okay, and this means you also have to explain the working mechanism of the devices, or you want the material to apply, okay, for, yeah, that is I mean. Okay, you also have to show the synthesis methods, or synthesis or fabrication of nanomaterial you use. Okay, even you can review several different synthesis methods. Of course, if you do like that, so you can have more chance to have a higher score. Okay, of course you can present only one method. It's okay, it's fine. Okay, but if you review this material can synthesize by several methods, so you can list it down and explain, so you can choose one of the best methods, okay, or one of the most popular methods, okay, or you, or the method you feel that is suitable for you, or suitable for uh, for the lab condition and so on, okay, so you or for certain application, okay, so you will present, okay, and then you also have to show a characterization of this material, okay, what is the particle size and how the synthesized condition is affect on uh, the property or the structure or the morphology of this material, okay, so you also have to present, okay, and the next content will be you have to show us the manufacturing process of the module. For example, you want apply the nanomaterial in sensor devices, okay, for sensor devices. So you also need to present, okay, what is a manufacturing process, okay, to fabricate that device, okay. You can give a briefing on that manufacturing process. So actually, this one I want to give you for okay, this homework, okay, but I will put it here with together with the presentation, okay, for, okay. So this is actually for the homework, okay, but so we including here, so you can present together with other topic, okay. So you have to present what manufacturing process of module or devices using nanomaterial. Okay, this is the nanomaterial which you choose. Okay, not in general. Okay, for a certain of nanomaterial you choose for a certain of material. Okay. Okay. Do you understand this requirement? Okay. Any discussion? Any discussion about or confusion about this requirement? Do you want to discuss? Okay, to make sure that you understand this requirement. Okay, so make sure that when you present, so it should cover, okay, full aspect of nano scale material, okay, involved to the presentation. So any discussion? Do you want to ask here? Okay. Nguyễn Đức Mạnh, do you understand clearly this requirement for presentation? Nguyễn Đức Mạnh. Mạnh not here. Đức Mạnh. Yes sir. Okay. Nguyễn Mạnh Dương.
Yes.
Do you understand?
Yes. But I mean, what about the about the process? You say that you can do the we have many many processing.
Okay,
many process
please.
Yes.
Please
Okay.
wait for a minute. Okay, it's very noisy. I will close the door first. Okay. Okay. Continue, Mike. Okay. Mike Giang.
Yeah.
Okay. What's your question?
Yes. About the synthesis method, if we do if we do in multiple synthesis method, does it mean that the detail we don't have to do it more detail than detail than the one synthesis method?
Okay. Okay. So you you don't have to so in detail process of synthesis. Okay, you just give briefing. Okay, what is this synthesis process? What is the advantage of this process, or what's disadvantage of process? Okay, so you don't have to show step by step how we process the synthesis process for all the methods. Okay. Okay.
Okay, thank you. Yes.
Okay. Okay, other question. Nguyễn Văn Bình. Nguyễn Văn Bình.
Yes.
Any question? No question.
No.
Trần Công Tân. Trần Công Tân, do you have any question about this presentation
No,
requirement?
I understand what you say.
Okay. Quảng Trà My. Okay, so if you understand about the requirement of presentation, so we will move to the topic. What topic? Okay, you can choose. Sorry. Okay. So here I list down several topics for you. Okay, you can choose. So the first topic will be covered for material for energy conversion. Okay, conversion. Okay, is okay. This is a topic. Okay, I can give you some example or some suggestion for material. Actually, okay, if I can require you, okay, you have to choose or select a material by yourself for a certain application. Okay, here I already give you some example. Okay, so it can be good for you. Okay, to choose or select. Okay, this is example. Okay, so for nanomaterial application for energy conversion can be thermoelectric material. Okay, so for thermoelectric material that can convert the heat, okay, into directly into electrical energy. So for thermoelectric material can be, for example, bismuth telluride. Okay, this what we call is a casterite. Yes, casterite structure is with copper, zinc, tin, and sulfide. Okay, and the third one can be this tin and selenium. Okay, and magnesium silicide and all these alloys, silicon, zirconia, okay, and so on, and material what we call is scutterudite group, also very famous, okay, in very well known in thermoelectric material and glass race and so on. Okay, so this is the material can be used for thermoelectric materials. So you have to choose or you have to find yourself. Okay, the nanomaterial. Yeah? So nanomaterial. Please remember that this is a name of compound. Okay, name of material. But you have to present. Okay, the nanomaterial. Okay, nanomaterial. Okay, this, for example, this can be bulk material. This also can be nano material. So you have to present your paper, okay, in and the methods they use to synthesize this material in nanoparticle size. Okay, nanoparticle size. Okay, okay. So this is for thermoelectric material. You can find by yourself, or you can suggest me, or you can propose. Yes, doctor. Okay, I want to use. I want to present this material. It's okay. It's fine. Okay, you can propose by yourself. Okay, but here's just a suggestion. But the topic will be covered. Okay, this you will represent in this given topic. Okay, the first, okay, for energy application. Okay, energy conversion. The second one will be photovoltaic material. Okay, this apply for solar cell. Okay, for solar cell. Here some example: silicon. Okay, and lab. Okay, so many different material here. Okay, you can see. So you have to on this week. Okay, you have to find by yourself. You look at all of this material and this application. Okay, and next week you tell me, okay, what is the material or what is the application of nanomaterial you want to choose. Okay, for the presentation. Okay, for example, next week you says, teacher, okay, oh, Dr. Long, I want to present about nanomaterial for energy conversion. I will choose a thermoelectric material. For example, I want to choose a nano bismuth telluride. Okay, it's okay. So next week I will freak you. You will your group will present this kind of topic for this material for this. Okay, application. Okay, so all clear? Everyone clear? Clear about my explanation?
Yes.
Okay. Okay, so also for energy material, okay, for energy conversion, okay, and we have similar. We have piezoelectric material, okay. Piezoelectric material, this means the material can convert from mechanical force, okay, or mechanical energy into electrical energy. For example, if you have one material, you can apply a force, okay. For example, hammer, you hit the material. So by just hitting, okay, by just impact of mechanical force, so it will convert that force, okay, just impact, okay, or just energy into electrical energy. So we call that a piezoelectric material. Very interesting. For example, some children, they have the shoe. You see, when they wear the shoe, they jumping, running. So you see, the lights will be emitted from their shoe. Okay, so that's one of the application of piezoelectric material. Okay. And for thermoelectric material, I explained a little bit about this material. This is also very interesting material. We can, oh, I'm sorry, after this, do we have other class?
No, we don't.
Okay, so let's finish all this. Okay. Okay, for thermoelectric material, it's a very interesting material. Okay, I am studying this material. Okay, because you know that the energy and environment is will be the more challenges issue on this 21st century. So we have our topic will cover the material is can convert, okay, or it can generate energy, or it can be store, okay, store energy. Yeah. So this the material, it can be generate clean, okay, clean energy, okay, and safe, okay, and safe. Okay, so maybe I explain to you about later. Okay, today we don't have much time to explain very detailed or interesting application of this material. Maybe next week I will continue to explain to you. But in this week, I just give you a briefing. What is this? What are this material? Okay, and the next one will be fuel cell. Okay, fuel cell material. Okay, this material using for what we call is a fuel cell, using to generate electricity for car. Okay, even for train also. So using this one, it can generate electricity. Okay. And the second one will be a nano material for energy storage. Okay, for example, material you to fabricate a rechargeable battery. Okay, with high capacity, you can charge the battery very fast. Okay, and you can produce battery with very safe. So this is also very hot topic now in VinFast. Okay, in Vietnam they also invest a lot of money in this kind of technology. Of course, more famous you can see Tesla, right? The electric car. So one of the most important in the electric car here, we have to have a very reliable battery. This means safe, okay, and have high capacity and very quick charge. Okay. Okay, we don't want to wait for the battery for the whole day or the few hours to charge our car. Okay, so this kind of technology, nanomaterial, can also push or can improve the working of this battery. Okay, And we also have hydrogen storage, okay, because hydrogen storage can be used for a fuel cell in car or the train, okay, because in the car or the train we want to use hydrogen, okay, is for the cell, it can make electricity. So how we can store hydrogen? For example, you know that hydrogen stored in a tank, okay, a steel tank, by you apply pressure, okay, so you can store more hydrogen. For example, if you press at 70 megapascal, so one cubic meter you can store about 15 kg of hydrogen gas. And if you make this gas into a liquid phase, so you can store more hydrogen. And now people want to make store hydrogen in solid state, okay, is even is have can store more hydrogen, okay. So you have to find out that material can store hydrogen. So this also the future for future technology also. And the third one, you have nanomaterial for sensor devices. So you have to choose or you have to find what is a nanomaterial applied for sensor. The sensor here can be a light sensor. It can be temperature sensor. It can be a sensor for detect a chemical or detect gases, and a sensor for humidity and so on, okay, and sensor, a lot of sensor here, okay, so you have to find the material by yourself. Maybe next week we can discuss, okay, next week you can come to the class, you said, oh teacher, I find this kind of material for sensor application, okay, if you confuse something, okay, about this, how is this material good for this kind of application and so on, so we can discuss in the class for in the next week, okay. And you can choose a nanomaterial for health application, okay, for health application. So for example, here have many nanomaterial can for health application. For example, nanomaterial or material can use to replace the bone. The bone, if the body, our body, the bone have some defect, okay. For example, cancer, some bone it can be cancer. We need to replace, or the bone can be a breakdown. Okay, so we have some material to replace. Okay, or to join the separate bone in our body and so on. So you also can choose that material for health application. Okay, and you also can use nanomaterial for environmental application. Okay, this one also. For example, I already give you an example to what we call is we clean the river, Tolik River by Japanese expert, right? So they use a nano particle, okay, catalyst can use for this clean environment. Or you also can use nanoparticle material structure. For example, titanium dioxide. Okay, that one can absorb CO2. Okay, so also can have to solve can solve the environment air polluted also. So and so on. You can propose what material for what application you want to present. Okay, so here just my suggestion for you. Okay, so any question here, okay, or any discussion? All clear? Trần Văn Hải, do you?
No idea.
No idea.
Yes.
No idea is mean you don't understand or what?
Yes, I understand for the suggestion of topic.
Okay. So in this week, you will find your own material you want to present. So so you can
Yes.
look from internet or you can read from the book, find your own material you want to present. So next week, you will tell me what material you want to present, and for what application. Okay,
Yes.
you understand. So other student, Trần Ngọc Nam, understand?
Yes.
Yes, understand.
Okay, so next week, you will give me, what material you want to present and for what application. Okay. So if you all clear, so we stop here. Next week we will continue. Okay.
Okay.
So I will post this topic and requirement on our team, for the reference. Okay. So we will stop here.
Goodbye, teacher.
Goodbye, sir.